Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It's my pleasure to welcome Burkhard Wolf from the ETH Zurich, where he's an associate professor in the group of David Bazin. So I know Burkhard actually for 15 years or so. We studied some time ago at TU Berlin together. He was is working around 10 years in the area of higher order logic and Isabelle. So in his PhD, for example, he developed a transformation calculus on base of Isabelle. Later he worked on embedding process algebraic approaches into Isabelle, and his recent work in the last couple of years is basically embedding object-oriented languages into Isabelle, and he has worked on an encoding of HOLOCL, the object constraint language, which comes with UML and Isabelle, and his talk today will tell us something about this, and in particular, like the title says, extensible data models with an implementation to a application to a little imperative language in course of that and embedding of OCL. And I would like to take the chance, there's actually a book. A draft book, the HOL-OCL book by Achim Bruckner and Burkhard, which describes in depth the all-over context or approach in which this work is embedded. So please go ahead.
Thank you very much, Wolfgang. Does anybody hear me? This fine with the mic? Thanks. So, actually, I'd like to give, as a general overview of my talk, I changed my original talk a bit since I got aware that actually some parts I'm working on are not very known here at Microsoft, for example, about the UML background. So I will give a brief overview and elaborate a bit on the HOL-OCL project, where this core work I'm presenting here is actually built upon. So after a short motivation, I will give the context of my work here, of this particular work, and then start about verifying OO program on top of the HOL-OCL system. We will find that actually there's a crucial problem to solve if you want to do this with standard theorem provers like HOL-like provers efficiently. You need a shallow embedding for program calculi that work for object-oriented languages. We will see a bit what the problems are. We'll found, in a way, a deeper problem which is behind this, namely the problem of finding a representation that is extensible with respect to proof theories. And then I will stack up we'll go back my problem stack and present solutions and come up to a final overall vision, actually, how this can be resolved for a very small programming language called IMP. So it's a while loop language with object-oriented constructs. Okay. Well, why OO programming? Object-oriented programming is the predominant paradigm of nowadays. Nevertheless, it turned out that actually verification of these programs is notoriously difficult. If you've visited, for example, the last HCAR and seen the most advanced theorem proving projects that had been done, they had been essentially done on various forms of functional programs. And there are quite a few approaches. It just took 2,500 lines Java code program, abstracted it into some functional code. Dude did a lot of quite impressive verification work on this functional program, and then went on later on to some results. But maybe that for the further future, this is not perhaps what you want, and I know that you do a lot of research actually to bring verification technology closer to object-oriented programming. What are the typical problems? Well, we have several features of object-oriented programming that are somewhat remote to actually what we have in the Platonic world of first-order logic or higher-order logic. There's the concept of state, of course, we are talking about. Then we have things like inheritance and subtypings, which make the situation complicated. We may have things like cyclic object structure, which represents in the mathematical setting to co-algebraic structures. And then we have something like exceptional behavior, which is somewhat omnipresent in object-oriented programming or object-oriented specification formalisms, which we have to deal with. All this together makes, leads to features and calculi that make them difficult to handle conceptually, but also automatically. Well, now I come a bit to the context. To see, because I know I became, from the discussion yesterday, I became aware that actually not too much is known in this community of our UML and what is actually there as a kind of attempts to model object-oriented systems in this community. So the UML is actually an open standard for object-oriented modeling languages. It is diagram-oriented, but it doesn't mean that there's no semantics at all. Depends, one has to say. So there are 9 different diagrams currently in the UML, like activity charts or like state charts or class diagram and many others, sequence charts. And they have, the essential thing is actually that they have a kind of normed abstract syntax. There are lots of commercial and non-commercial diagram editors available, so that can be, they are really liked by engineers. They like this kind of diagrammatic notations, and that's why there is quite a lot of use. This means also that there is a particular methodology behind. So one likes to have all these diagrams, represent them in a quite structured way, and then define compilations towards code. This is the idea behind model-driven architecture. So there are lots of frameworks that allow you various transformation of these abstractly described systems and to describe some more or less formally described transition to code. Actually, 3 diagram types have at least partially a formally defined semantics. So essentially, activity charts, state charts, more or less, and class diagrams. I'm talking about class diagrams with OCL. So there is a way to annotate class diagrams with a particular textual language called object constraint language. And you can describe in this language actually class invariants and pre and post conditions of operations. You can use OCL also to annotate state charts for state invariants and guards. So OCL has a quite operational flavor. This makes it also difficult somehow to reason with it, but it makes it easy to evaluate and to use it for animation. What is at the moment typical, that is there's no actual formal link between operations and methods. So in the UML class diagrams, you may have methods A, B, C. And, well, they are not methods, they're called operations. And you may associate to operations with pre- and post-conditions methods in various programming languages, which could be used for code transformation or whatsoever. But so far, it is intended that actually a method should correspond to its operation specification. But so far, there is no clear, defined connection between these two. So for a couple of years, we started this HOL-OCL project, essentially for the class diagram part of together with OCL, which we thought it would be a good starting point to actually deformalize object-oriented modeling itself, and in a quite clean, theoretical-based way. So as a conservative embedding into something well-known. Namely in something like higher-order logic and the various theorem provers that are out in the world for this type of logic. It's also an attempt to develop actually a proof methodology for this kind of modeling and for programs over these particular models. How does the HOL-OCL environment look like? Well, it consists of a tool chain. You have at the front end typical case tools in which you can design and write these particular diagrams. At the moment we support Argo UML, which is a public domain standard. You can design your diagrams there. Then it runs through a kind of processor that does the type checking for OCL. At the moment, OCL is a textual file which is just associated to the specification, which is injected, but it could also be managed by these case tools. There are ways to integrate OCL on this level. And then actually it goes into the HOL-OCL system, which we built on top of Isabelle HOL. It has, a number of own specially decision procedure or tactics that allow some automation of proofs in OCL. It has a quite large library, so OCL talks about sets, sequences, and so on in a typed way. And it has some component with the OCL package, which is actually able to parse the XMI representation of such a class diagram with this specification elements, and to convert it conservatively, as I will show, into a data type theory, which allows for reasoning over this particular theory. And on top of that, you have a proof general. This is a proof GUI, if you want, a very weak form of integrated proof environment, which allows you to edit and to prove on the fly interactively proof scripts or proof documentations, one has to say, on top of the system. An example. So one can describe the following class diagram, starting with a node having the attributes integer left and right, and you can have a colored node which is just inherits from node and has the additional attribute color. And this is the running example of my talk here, so simple, but you will see it in various forms again and again. So one can now associate with this OCL language to this particular diagram. Here it's essentially said import associate to the node from the diagram the following invariant, namely that any I field should be larger than 5, and that any C node should actually have the following invariant, namely that the color of the left son should be different from the color of the father, and that the color of the right son should be different from the color of the father. This is the invariant which I expressed here. Now OCL is a 3-valued logic. So what is implicitly going on here, and if we state that this is valid, and if we know that all these operators like injection or coercion, which I made here fully explicit, you have not to do this in OCL. Usually there's an expansion mechanism for this, but I made it fully expanded everything that goes on semantically here. Since all these operations are strict, this means that actually this equation must be defined, this selection must be defined, this whole path must be defined, which means that all these projections here into the state and dereferentiation must be defined. So from the point of view of a specifier or a modeler, 3-valuedness has some advantages. I know that lots of people coming from theorem-proving communities hate 3-valuedness, and sometimes there are good reasons for this. But from the modeling point of view, one can see that actually if you have something that dereferencing might go wrong and it might be something like a bottom or an exceptional element, then building this inside and wiring this deep inside the logic has some advantages, one has to admit. So we have to cope with it. Yes?
It has to be defined. Does it mean that, can you say, what does that mean now? So if left is not defined, for example, left is null, no?
If left is null, if this representation wouldn't work, then this whole thing would be bottom. Then this thing here would be bottom.
Is this formula then satisfied or ignored or not satisfied?
This formula wouldn't be valid. Valid means it would not evaluate to true.
Okay. Would that be a violation of the invariant?
Yes. It would be considered a violation of the invariant.
The termination case is missing here, probably, no?
There is no such thing, such termination. There is just...
Because then this formula would say that every tree must have a left and a right child, no?
Exactly.
Which means that it's an infinite tree.
Or well, not necessarily. We will immediately see a model, namely this one here, which is actually a model to the thing. It just says that these references in here are defined. But since we can have cyclic structures in object orientation, we have an object structure like this, which is an admissible model by this invariant. Mm-hmm. Okay, do I have to explain why this is a model? No. Okay, we can have also, of course, weaker forms in order to avoid this. Yes?
If you don't want a cyclic structure, then you would have to write the defensive specification.
Pardon?
That if left is not null, then blah blah blah. Is that the way?
Yes, I will immediately show a weakening of this particular invariant. By the way, I forgot some little fact which is also implicit in this specification. And if we go on and translate this thing in a two-valued world, we have to make it explicit. The fact that the dereferentiation of color at this position worked meant that actually this whole thing must be a colored node. So it must be of the kind colored node. And this means that this thing is actually a recursive predicate. So the left and the right sun must be colored nodes. That's what this specification implicitly says. And this means, well, we could not leave out these pointers and point to something self, or we have that always these two values here have to alternate. So it's not that the suns, the left and the right suns would not have, there's any means that they could avoid this to not underlie this invariant.
So you're using a standard OCL?
Yes, yes. So plain out stratified, any kind of syntax embellishment are omitted. So it's really plain OCL as you can have it. Mm-hmm.
Go back to that invariant. Why do you have to do all of this OCL as type on the left-hand side of the equality?
No, you don't have
not on
to.
the right-hand side.
Don't have to.
No, you said that, but I was wondering why you wrote it on the right-hand side. You didn't bother for self.color.
Well, the node, the left is actually an operation which is defined on nodes, on the type node. So you have to cast this thing, actually the self node, so which implicitly means that it was a colored node, to node. Then you can dereference it, just as a typing issue here at this position. Then you must cast it back and dereference a color. Of course, a decent type checker nowadays would make this behind the scenes. But as a semantic representation, what's going on, we have to be that precise. Okay, there are weaker forms of this invariant. Of course, such an invariant you wouldn't be able to establish at once in an imperative programming language. There would be no miracle that allows us to generate 3 objects at once and to wire it in the right way. So we need actually also weaker forms of invariants. So the way to do it would be, as already someone suggested, Adam suggested, that actually we can say that the left, if it is, it may be undefined. So also if you do all the embellishment away, it simply means not OCL is undefined. So the left sun should be defined, this means. If the left sun is defined, then it must satisfy the following equality. If the right sun is defined, it must satisfy the following. But if it isn't, the specification has nothing. So you can have a node with no defined links at all.
So
with this would satisfy.
Logic, you can have an arbitrary expression
Mm-hmm.
that just delivers button,
Mm-hmm.
and then you can test whether
Yeah.
this is basically turn it into a valid
Yes.
expression again.
Yes.
So where the undefined can be deep inside the expression. It doesn't need to
Can be. Yeah. Can be. So you have more than just another dereference operator and then go back. You can just say, oh, the whole thing must have been gone well. And this means that actually you have quite a lot of expressive power. There is some abbreviation power in this kind of notation. Okay, So we'd like to represent this kind of modeling. Okay, and we have methods with pre and post conditions, but that's the standard. So we'd like to represent this stuff actually in well-established HOL provers like HOL4, HOL-Lite, Isabelle HOL. My major machine is actually Isabelle, so I'm an Isabelle HOL hacker. So I chose this one, but essentially this carries over to all these systems. Actually, there are meanwhile importing functions. You can convert an Isabelle HOL theory in HOL-Lite and let it check there. So these systems are somehow converging. And if you don't trust Isabelle but trust another prover, you could compile these proof objects. That's it's merely a technical task nowadays to do this kind of work. What we have to do is actually, what we don't want to do is we have actually a definition of the semantics, and we derive all these calculi for which we then develop automated support for this particular type of formula and this particular type of reasoning. So in a way, you might reproach us to be very foundational. So we are very interested actually. We have very much a bottom-up approach, while as far as I understood in the Boogie project and similar projects, you have much more top-down approach. You have already a particular assumption on the underlying machinery and under the operation or denotational semantics of C#. You develop your calculi, you develop your verification. You start with your verification condition generators, assuming a particular operational model of the underlying language. Well, we go the other way around. We have a particular denotational semantics of the underlying language, and then we derive the calculi, and at the very end, even we would derive a verification condition generator. So, in order to make this work, the crucial thing is that one can embed in a HOL prover all and everything. That's not the point. In order to make it a tool, it must be a representation of a particular type. It must be done in a particular technical way. Otherwise, it can be done, but it's the maximum length of a program that was verified, for example, on the Nano Java encoding in Isabelle HOL was a program of 15-line length. So, and I think that's it. You will not go very much far beyond it, because simply the complexity that is connected to certain aspects like typing are so complex that it hampers all the way, all the proofs, and all the automation of the proof work. So what has to be done is that object-oriented types must be represented one-to-one in HOL types, and that actually you have a representation of binding which follows the style of higher-order abstract syntax. So just as an example, this is a mathematical notation of the for-all operator in OCL. If you want to do something like this, X should be one of the possible nodes, so one of the nodes that satisfies the invariant of node that you've seen. Then some predicate holds. This should be converted or just be a syntax for the following thing. Well, we have an operator for all, which is now a constant in the theory HOL-OCL. And, well, it has an argument which is just a typed set. It gets the right type that was actually a consequence of the class diagram. And then you want to apply it to this particular lambda abstraction, which is just the notation of this particular binding here. Meaning that the internal mechanisms of Isabelle to handling binding resolution, higher order resolution, and so on apply here and can work out behind the scenes. Why this particular type of embedding? Well, this makes HOL provers reusable, and it also allows for a very higher efficient deduction. This means that typing is already done once a deduction starts. And it's not part of the calculus in side conditions that has to be resolved on the fly. Yes, please.
Where is A used in the second line?
A? A is just... well, this is... It should be... That's the name node. Sorry, this is an error. You're right. It should be A. Instead, erase A, just say node. So the constant node, being of node set, characterizes the set of all nodes that exist that satisfy the invariant. Sorry.
So for all takes two arguments.
It takes two arguments. It takes this particular argument,
Okay.
and it takes this argument, lambda abstracted.
And the type of X, does that have to be related to A?
Yes. This type here, so the for all type has the type, so this alpha set goes from x dot alpha to px, which is a function to go from alpha to, well, some representation of Boole. This is the so-called, this is the core of what is called a shallow embedding.
So you've taken X of type alpha and then, no.
Do we have a blackboard? So for all would have the type for all alpha set arrow alpha to, well, bool, and that doesn't work. We need to bottom it up. Bottom, yeah.
All right, so it's just relativizing the quantifier to the smaller
Yes.
domain.
Yes. So we don't have something like for all, which would be a deep embedding for all, like string, and then here cross term to term. Something like this would be a deep embedding. Meaning, okay, we define in a way the abstract syntax structure of terms, but these terms represent all sorts of data which couldn't even be ill-typed. If we do this is more in a way more general, but this would mean that in all kinds of calculi we have to have side conditions saying, okay, this particular term must be actually a well-founded term in some signature, and this means, and then we have the deduction has at all the time deduce actually if something is well-founded. We want to avoid this. That's why we need a shallow embedding like Isabelle, HOL, for example, in Isabelle is. It's a shallow embedding, and that's why it's efficient. How can you do this? Well, if we want to do this, if we want to have this neat and strong association between types, then actually we run immediately into the following technically very relevant problem. Of course, we have class diagrams, and in practice we will extend them all the time during the development of a larger project. So what does this mean if we represent class invariant as states on in this particular typesetting? Well, we could, for example, develop the state, the underlying state of a program by the following partial map. So we have object IDs or reference or pointer, just as you like, as a partial map to some universe, where this universe, in the original case, just consists of nodes. So imagine we had this little, in our standard running example, we had this class diagram. First we had the node, and then we developed the theory, and then we built up the C node, we added the C node, and then we want to continue with our theoretical work. So if we start with this, then at the original situation, we would have the following universe of objects, just consisting of the node type. This would mean actually we have, it's a Cartesian product of the integer and two references, okay? And the second case, we need the sum of these two types, because now we have two objects, and of course this could be in the state either this object or that object, so we have to represent it that way. And then we would have this particular representation of the second universe that we get after the second insertion of a class into the system. Okay, unfortunately, these two types are incomparable. So any property that we have proven over this universe will not hold any longer on this universe. So this kind of representation of class diagrams immediately breaks down any modular attempt to build up larger proof theories. And this is a very severe problem for systems like the loop tool, developed by Bart Jacobs, the other Bart Jacobs, not the Bart Jacobs who is visiting us here. And for example, for Jive, who also directly compiles into Isabelle theory by enumerating a class direct by an explicit sum of objects. And whenever you do something with it, immediately you have to reply everything that you did. So what is the solution to this? So I'm now in the core problem, and how do we solve the core problem? And then I will come up with some solutions, hopefully. So what you could do is you can say, okay, make my universe extensible, meaning that, okay, we have the node type. So far the class diagram is fixed, but there may be further extensions to these node types in form of inheritance classes. So we may have put in a hole in our universe. And actually there may be also an alternative to node types. There may be also other similar alternative types added in the class diagram. So this would be represented by the plus beta polymorphic variable. And now the trick is we have added enough holes in our universe, and whenever we plug something into a hole of the universe, we just make technically sure that there will be other holes in order to maintain the process and keep the process alive. So for the second universe, then we have actually, we can actually build in this particular hole, we plug in the C node delta part, so the extension part, just the color part, and add a new way to add new further information, plus alternatives, plus alternatives. Now the trick is, actually this universe is a type instance of this universe. So that meant whenever we have presented a proof over this universe, we implicitly made already a proof over all possible extensions of this universe. This is the core idea. This is great news.
Fairly abstract.
Pardon?
The proofs at the high level will be fairly abstract.
Yeah, I will show you what kind of properties you can already generate and generate them automatically. Of course, you cannot do all in everything. So if you're talking about imagining already something like overload resolution in open class diagrams and things like that, we get phenomena that where you actually cannot prove something. But we are not that far. We're just at the basis.
So this is a way to allow for subtypes. Does it also allow for multiple inheritance?
No. Our mechanism so far does not support multiple inheritance. There had been people in the scene like Thomas Santen, who presented a work quite a long time ago. He worked actually with quotient constructions over these sums. And then you can achieve this effect. Maybe it can be worked somehow. We don't know. We didn't consider it. So far, our system does not support multiple inheritance. So what is now needed? Of course, having the whole building this kind of representation of objects of a class diagram is a quite tedious work. You don't want to do this by hand. And you don't want to prove the elementary theorems over this particular data type theory by hand. This is far too tedious. What is needed is a kind of logical compiler that takes this data type description and compiles the definitions, the conservative definitions for this data type theory out, and all the kind of facts that follow from it. In principle, this technique is well known in the world of hole provers. All these hole systems that I suggested have this kind of thing in there. It's called a package. It's a data type package. And this is an add-on on the inference engine that does all this kind of reasoning over data types automatically. And what is standard done is that actually you freely generate initial algebras, and what we do here, what is needed, since we have to do with cyclic structures, we have to produce freely generated co-algebras. And this is done conservatively in this extensible universe where we have to represent the class invariants. Okay, so this is the plan. Now how can we actually proceed to do so? This invariant you have seen is now represented in the two-valued whole world as a recursive set initially, and later on we will derive from there via fixed point construct, the greatest fixed point construction, actually the set of all admissible nodes. So how is this done? So we just build some abstraction. Recursive. It's going to be the core of the recursive predicate. So we talk about essentially the X parameterized set over object self, which fulfill the following thing. This essentially abstractly represents that the node invariant should hold. So this should be an element. If you convert it, cast it to the node, then it actually should fulfill what should be in the set of all admissible nodes already. And then, okay, we have to wrap around that everything that was implicit in this revalued notation. So we have to say that self.left.color is defined, self.color is defined, self.left is defined, and so on. Self.left must be actually in this particular set. So here it becomes the recursion, the implicit recursion must be made explicit. And we have that actually this particular equality finally holds, inequality, sorry, finally holds, etc. So we have to make all of this which was implicit in this 3-valued world explicit in this 2-valued world. We get this recursive functional, and we can just define the greatest fixed point construction over this. And now certain sets become the same. So, for example, the sets that satisfy the kind of that are in the kind of C node is the same as being the set in this particular greatest fixed point construction. GFP is one operator that comes from HOL. Now we have a HOL construct that represents this set of all these admissible attributes. And as you see, this here is a conservative definition. So there is no recursion in here. It was just a function definition that abstracted some things away. And since we have the greatest fixed point operator defined somehow already in the library of HOL, we can build this set in a definitional way. And define from there concepts like is kind or the invariant of C node holds. Now we know it, what this means. Of course, the other invariant, the weaker form, can also be represented in that way. The only thing that is changed is that we have here this additional implication that weaken this kind of abstraction. And the whole construction works the same. Okay. From this internal definition, we can now derive that actually the 3-valued presentation of our theorem, the thing that the user wanted to see and gave into the system initially, can be derived and is derived automatically behind the scene. So now the recursion in here doesn't hurt any longer because it is derived from a conservatively defined principle. And again, we have now this particular form, and we can derive the infrastructure for is kind, is type, and s time, so all the coercion stuff that is related to object orientation. We can do the same thing for invariant, the C-node2 invariant, so the weaker form of the invariant. And we can derive theorems like inherit. So this would be one of the theorems that hold once and for all. Tom, your question, what actually holds in such a world? So this type of theorems, for example, hold once and for all. Something like, okay, that C nodes casted are actually nodes, or that if I have two classes B and C that inherit for some class A, that they are actually disjoint. There's a distinctiveness theorem, or that this stronger invariant actually implies this weaker invariant. Things like that.
Distinction
derived from this construction before this is parameterized with the holes.
Yes.
Type definitions with the holes.
Yes. So you cannot have an exhaustion. You cannot, without finalization your class diagram, you cannot have an exhaustion theorem saying that okay, it's the sons of some class A are either B or either C. You cannot have this. You have only that they are pairwise distinct so far. If you finalize this diagram in this particular point, you will get an exhaustion theorem which says, okay, it's one of them. And would you allow either co-induction or induction principles if you add further information in the specification? But so far we have only this. If you add new stuff, then you get more. But this is the core what you actually get so far automatically. Now, this is already something that is actually at the very end nice and relevant for the program verification, because then at some point we need later on some step like, okay, we have done several program steps, wired some objects via assignment, and later on we accumulate from this weaker invariant additional information, then we make the step that actually the stronger invariant holds after certain steps. Moreover, we can generate also automatically the whole infrastructure for programming-related operators. These are not part of the OCL, but you have not something like the creation mechanism for an object, or an update for an eye, or a left or right, and a color. This actually is not supported by our current release of the system. So this is, we had, at the moment in our example, we did this by hand to derive the theory for these operators. Okay, so this had been the core. We have now a mechanism to define class systems, to annotate them with invariants, to annotate them with pre and post conditions. I haven't shown you anything about pre and post conditions so far. What can be done on this level is already we can do refinement and consistency checking of class diagrams. We can do lots of things that have to do, for example, with a model-driven architecture. So if you transform a model into another, you might want, for example, do this transformation only by generating some proof obligations, and if you discharge them, these proof obligation in OCL, you know something more about this other system. For example, another paper that we had presented at the last models was you have a secure UML technique. This is, you have a business logic of a certain system given by a class diagram annotated. You add the security model, we'll say the access control model, and then later on you have proof obligations that actually allow you to establish that this enriched system actually behaves the same as the original system, provided you have enough privileges in the underlying security model. So it doesn't happen something like an operation had been modified, it worked somehow, and then something is broken, you didn't get access to this or that attribute, and the system is left in an inconsistent state, for example. These things can be ruled out by this scenario. So far, we do not have a programming notion, not a notion for methods. That's what I'm going to present in the last 10 minutes, briefly. What we did is we took this imp language, which is well known from the Winskill book, which is also available. There are standard developments for it in the Isabel library. So we took this theory actually and extended and modified it that it would work for this kind of object-oriented data models underlying. And this would mean that we have, command language. We have to give a denotational semantics, which takes the COM elements of this language to lifted states. Lifted, that means, okay, there can be something like a failure state after occurring some exception by some access into some attribute, and it didn't work. And, the exception wasn't caught somehow, so the program just reports an overall exception. So this can happen. And, of course, this is a relation over this particular type of things. There's a paper, I give the reference later on for the precise definition. I cannot go into details here. Huh? COM is just the syntax, command syntax of while, of this while language. Do I have it? Yeah, here is it. This is COM. So you have skip, you have the sequential composition, you have a command, you have the if then else. Besides here, we have the update operations. Well, this is the slot for building the update operation. We have an assign operator, and we have a while operator. That's actually what the syntax is of this particular language. And from this kind of denotational semantics, we can now define the validity of Hoare triples in standard style. This is standard definition. So a triple is valid if S and T, two states, which can be Arrhenius states, are in the relation produced by the denotational semantics of the program. This means that actually if P has, and if our assertion P holds over this state, then Q should hold over this state. And from there, hooray, we can derive, we did derive actually this particular Hoare-Logic that can treat with exceptions underlying. And here, if you look into the consequence rules, you have also a situation where you may strengthen and weaken invariants over states. This is where it happens. And you can reuse lemmas that had been generated from the data type package, where you had introduced stronger and weaker forms of invariants, which actually this implication had to be verified by co-induction. So internally for this step, there had been used a co-induction to establish the relation between these two invariants. I cannot go into too much details. In the paper, there's actually also very little program which shows exactly this effect. You build up a larger structure which finally satisfies a quite strong invariant where everything was defined. This is what you can establish in this work here. In Boogie, actually, as far as I learned, you have this particular flag that shuts off an invariant, a global invariant, for a time. Then you can reason over this part. And later on, at some point, you want that actually, you have to check that actually, if you shut on again this invariant, then you achieve this point. This could be in our system understood as an assertion that from then on, you want to have that the stronger invariants hold. We don't have only, we cannot, or we support in our system various forms of invariants, stronger and weaker ones. And during the Hoare-style proof of the program, you can play with this. Can assume stronger and weaker forms of invariants. Okay, I have to conclude. It's definitely near 1 hour. So what you have seen is a paradigm for the safe construction of OO verification tools. The core of it, that the whole thing actually technically works, is this extensible universe construction that you need. Supported or used internally only by this data type package, which I discussed and briefly mentioned what it actually does. There are, we derived on top of this version a Hoare calculus with exception that allows OO program verification. What has been done in other Isabelle HOL-related projects was the derivation of a verification condition generator. For IMP, there's a standard element in the library. A more competitive version was actually produced by Norbert Schirmer for a larger fragment of an imperative core language with procedure calls and mutual recursion and stuff. This system is actually used for applications. And our future vision is actually to produce also something like this on the grounds of actually derivation and safe embeddings. Okay, perhaps also the literature. There's the HOL-OCL page. It's registered, so if you are interested, you could probably look up this page later on. There's the HOL-OCL book, which is online. This is at the moment a technical report, but we plan actually to extend this further. And then there is also the paper that was presented here at the SVV workshop at the HCAR on this particular data type construction. So this is it, essentially. Are there questions so far at the moment? Then I'm going to make a very little demo in order to see that actually to compile the diagram that you've seen takes just 10 or 15 seconds or so. Any questions? No? Okay. So this here is proof general. And unfortunately, the font size we had to trick a bit because, as I said, my notebook doesn't understand very well, or doesn't communicate very well with the beamer here. So this is one of these examples. You have actually the theory digraph. This is the ESAR format in which you type down in the Emacs proof specification documents. So you can add here in various text, which is actually later on converted to LaTeX text. So you can include here various forms of LaTeX in order to present the documentation. I just check the logic. I would put it to HOL-OCL. So we base this session here on the entire HOL-OCL system. We say just next, and what the system does is it starts now Isabelle, hopefully. Yes. Okay, now the Emacs asks me lots of questions, what I should do with all the... Then this is typically proof general. I've seen some of you have never seen proof general, that's why I go in this detail. So there's this upper part of the buffer which is fixed, you cannot edit it anymore, and it is transferred to the system which has checked. So the blue part is actually which has been done. The other part are just editable text, and the way to proceed and to interact with the system is you edit, you add some new assertions, you change your model, you try to get it through. If the Isabelle accepts, fine. Otherwise you backtrack, you edit any more, and so on. Here I stepped just through because the core I wanted to show here is this. This is the loader. So this is a part of the HOL-OCL. Here the diagram is actually loaded, and below the system now generates all this kind that I've sent you, the stronger, weaker invariants, the data type theory, and so on. And we are done. No, we are not yet done. It derives, there are actually 250, for this thing, 250 definitions involved internally in the system, and it proves 25 theorems or so with this data type theory so far. And now we are done. So this is it. Now you can prove facts over the system like, okay, here's text. Sorry, can we continue over this thing? Actually, there are description over proofs here, but I don't want to go into detail. Here are lemmas now, which talk over things like this. Just go to here, and here you can now establish facts over conversions between various forms of equality and strict equality and some form of deep value equality, which is also present in our embedding of OCL. And here some facts are proven about this. So and you go through this kind of document, you work this way. This is the way the system proceeds. I cannot go into details of proof procedures and so on. This would be a completely different talk. You may invite me, but I'm sorry, that's it for the moment.
So this lemma contains OCL-like syntax.
In Isabelle, right?
Exactly.
So it's kind of parser you edited. It's not real OCL, but as in always in Isabelle you can narrow
It's
something.
our Isabelle representation of OCL. Yeah, exactly. We have used a mathematical notation because we hate to, since we work interactively, we hate to use this very, very spacey OCL notation. Probably for spec sharp verification people one day they will also do pretty much the same thing, because if you really work with this kind of formulas, it's very hard if they are so vast.
For proving this lemma.
Yes, so you use the C node 2 invariant of X, that this implies something over C node 2 invariant of Y. I do not want to go into the example, just to give you a feeling what is going on.
And you have written this tactic basically there, and once you have defined the tactic, it will find the proof again.
Yes, up to the state where hopefully gets to no conclusion solved.
Your proof engineer's job was actually to define this tactic down there, apply sim up, degraph, C.
Yeah, this is actually a standard tactic from Isabelle, but there are others in here which I'm not going to want to discuss here that had been developed without and that tackle typical deduction problems with OCL. So three-valuedness, the reasoning of definedness, propagation of equalities within particular states in the same state, things like this. The problem is that the internal logical equalities, these equalities here are not congruences anymore, they are somewhat local congruences only.
Which brings me actually to another question. So this
three-valued logic, how much does it make things harder for the proof engine? So is that, can you quantify that, or is that some explosion? I think the first thing is that happens that actually once you have translated this, you have an explosion of certain explosion of things you have to prove for every sub-expression that it's defined and so on. Is that the problem in finding?
The theoretical results are known quite a while ago. From Handel, essentially, there is an investigation about the complexity of tableau provers for three-valued logic, and these results are extremely negative. I'm not that sure that actually this led many of this group that are working off the key tool, for example, does also quite similar things as we did here. And they came up to the decision they don't want to have three-valued, and they simply kicked it out from the OCL language. In our experience, but it's still very early to say, you may have in certain proof states quite exponential blow up. This has to do that any path subpart actually that you get definedness assertions over this. So OCL is in a way very, very compact, especially if you have it inside of class invariants. A very compact notation. In some situation you have to expand it, and this gives an exponential blow up already in the proof states. So for the overall procedure, again, it seems to be quite negative. On the other hand, all practical results that we have so far, we have not so much experience with real die-hard verifications on this level for this kind of modeling. So far we had been mostly concerned with bringing our engine right and building the library right and building this machinery I presented here right. So we didn't do substantive case studies. But so far we have the feeling that since the three-valuedness is essentially limited to the logic core, so and or else applies and so on, and since all other operators are strict, this is not really so bad. And definitely a lot of automation can be done. So either you expand this notation in a two-valued world that at least we do internally in this package, or you live with the three-valuedness and you keep the compactness. It is a question what way to go depends on each of these decision procedures that I have built on top of this, which are not part of this talk here. But yeah, our impression is that actually it's feasible to live in this world, although the theoretic complexity results are highly negative. Any more questions?
Do you think in the end this system will be usable by non-experts? So meaning that you can bring the Isabelle automation to a level where...
I do not believe in general that verification can be done, really substantial verification can be done full automatic. I do not believe in the push-button dream, sorry. So there will be also always a separation between people who develop a system and perhaps annotate it with specification, and others who analyze the system. I do not expect that actually also in building construction we have architects and we have engineers and we have bricklayers, and that we could have a bricklayer that also do the static computation over a building. This is, I think, not a realistic dream. This is not what I think in the far sequence we will have analysis of real systems. So there can be a lot of automation, of course, near static program analysis, of course. And this must be done, and it's very useful what is done there. But in establishing real theorems over programs involving induction, involving data types and data type reasoning, I do not believe this for a very, very long time.
Well, I have heard the argument several times that in software development, bricklayers are actually the compilers, not people. So architects might end up writing programs in a high level, and then compilers lay the bricks for them.
This is an utmost nearly Marxistic view of the development. So anyone is empowered to do anything if we have enough tools and if the underlying technologies are well set for. Maybe you're right, I don't know. Let's see what the future brings us. I can only say so far I'm very skeptic. I think that we need to be sure that actually we will have different people. That's my vision.
I said it's an argument I have heard.
Yeah.
You're saying I'm right, they are right, probably.
Mhm.